Sesim geliyor mu arkadaşlar? Tamam. Sorusu olan var mı? Okay. No questions. Let's continue. We are here. Example. So let's try to find the eigenvalues of the last matrix. Okay. Find the eigenvectors and eigenvalues. Find the eigenvalues and eigenvectors of the last matrix of A in last example, let's say. Okay, so what do we do? So what we do is, first of all, okay, the eigenvalues will be the roots of this cubic polynomial, okay? So eigenvalues are roots of the cubic polynomial. Lambda cube minus 6 lambda square plus 11 lambda minus 6 equals 0. Okay, in general, you know, we don't, I don't know the formula for how to solve this cubic polynomial. So there is a formula for this. So there's a formula for general cubic polynomials, right? But we never teach in high school, we don't teach in university, we don't teach in grad school. I mean, nobody knows it. But some computer systems, algebra systems know it. The reason is the formula is a little bit complicated. It's hard to memorize, and usually there is no reason for that. So what we do instead is we first look for a solution by inspection, okay? So for example, for this one, so let me say something about this. Okay, so if we factorize this like this, lambda minus lambda 1, lambda minus lambda 2 times lambda minus lambda 3 equals 0. And you see, so lambda 1, lambda 2, lambda 3 are the roots. So if you expand this, you will get something like this for a cubic polynomial. Lambda cube minus, what will we get? So we will get something close to the quadratic case, which is the sum of roots times lambda square. And then we will get something which is not, which does not appear for quadratic polynomials, lambda. And then finally we have minus, so the last term is really minus the product of 3 roots, okay? So for quadratic polynomials that we know, so the constant term is basically product of the roots, and for cubic polynomials, the constant term here is minus 6. It's basically minus product of roots, okay? So product of 3 roots is 6. So we wonder whether we can find like an easy solution, an integer solution, okay? So here, so what does this mean? So this means the product of roots is really minus 6. So any easy solutions? So what can be integer roots? Integer roots can be like minus or plus 1, 2, 3, and 6, right? So integer solutions. We don't know if this polynomial has integer solutions or not. We're just checking, okay? Integer solutions are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, okay? So these are the only possible cases. So are any of these roots? So for example, we can check whether 1 is a solution. If we plug in 1, 1 minus 6, plus 11 minus 6, is it 0? Ekranı büyütebilir miyiz? Ekran küçük mü şu anda? Ekran her zamanki gibi değil mi arkadaşlar ya? Birazcık küçük. Valla her zamanki gibi şu anda ama. Bu arada bu ders notlarını da internet sayfasına koyacağım arkadaşlar. Oradan daha sonra bakabilirsiniz. Ekranı büyütmek gibi bir opsiyonun burada olduğunu şöyle yapalım. Şöyle tutayım o zaman. Şunu çevireyim. Okey, böyle yapalım. Oops. Okay, so we were at this line, right? Böyle daha iyi. Okay. So integer solutions are plus or minus 1, 2, 3, 6. So we have looked at the case whether lambda equals 1 is a solution. So we're just checking, okay? So what if I plug in lambda equals 1, 1 minus 6 plus 11 minus 6. So this is 0. So lambda equals 1 is a solution, okay? So we can see that this is lambda cubed minus 6 lambda square plus 11 lambda minus 6 equals lambda minus 1, because lambda equals 1 is a solution, times there will be a polynomial here, a quadratic polynomial, okay? So it will be a lambda square plus b lambda plus c. Now I can try to find a, b, and c, okay? So what? How do I find a, b, and c? First of all, it's easy to see that a is 1, right? A must be 1, because this will be a times lambda cube equals lambda cube, and a must be 1. Okay, so this must be 1. Let's write it here. A is 1. So can we find, so what are the equations for b and c now? So let's write this. So we get lambda cube. What are the other terms? Lambda cube plus, or let's write a lambda cube, okay? So that we see that it is 1. And then what are the lambda square terms? Lambda square terms, we have minus a plus b, right? So these are the only terms. What is the lambda term? Lambda term is c minus b. And what is the constant term? Constant term is minus c. So from here we can find all the solutions. So there's only one solution, which is a equals, a must be 1, as we said. B must be, so b minus 1 is minus 6. So b is let me write b minus a is minus 6. So b is minus 6 plus a, which is what? Which is a is 1, right? So this is minus 5. And let's look at c. So what is the, so minus c is minus 6, which gives us c equals 6. So this equation is also satisfied, right? 6 minus 5 is 11, so it's satisfied. Okay, so our characteristic polynomial is this one. One root is lambda minus 1. What are the other roots? So it's lambda squared. What is b lambda? So minus 5 lambda plus 6. Okay, so I can further factorize this. So I know that the roots are lambda equals 2 and lambda equals 3. B7 mi? B eksi 7 mi? Yanlış mı yaptım ya? Eksi 6 artı 1 eksi 5 olması lazım. Okay, no problem. So what are the eigenvalues? Eigenvalues. So eigenvalues are the roots of this polynomial. So we have 3 eigenvalues. Lambda equals 1, lambda equals 2, and lambda equals 3. So these are the 3 eigenvalues. Now, okay, so here is the more time-consuming part. We need to find the eigenvectors. So for each eigenvalue, we will try to find the eigenvectors. So let's start with, okay, let's write eigenvectors. So we start with lambda equals 1. So what happens if I plug in lambda equals 1? Okay, where's my matrix? It's somewhere here. Okay, so so what I will do is I'm looking for 1 times I3 minus a times the vector x equals the 0 vector. Okay, so what does this mean? So let's go back to the matrix A, or I minus a, lambda minus a. So here what I will be doing is, let me erase these. What I will be doing is plug in lambda equals 1 here. So let me copy that. Let me copy this. Yeah, copy. Let's go back here, somewhere here. Let's paste. Okay. So I will put lambda equals 1 here. So lambda equals 1. So what do I get? I get 1. I get 1. 1. And I get 1 here. Times the eigenvector. Okay, let me erase these things too. X1, X2, and X3 equals the 0 vector, 0, 0, 0. Okay, so how do we solve this? So I plan to do it only for this eigenvalue, okay? For the other ones, I think I will skip them, so it will take too much time. Minus 4, minus 2, 1, and 4, and 1, minus 1, and minus 4. And I write the 0 vectors here, 0, 0, 0. Okay? Any questions? Okay, so how do you find x1, x2, x3 from this equation? So you see the second line and the third line has a relation, so I can make that line 0. So in particular, if I if I, so what is the operation I'm doing? So I'm using minus row 2 plus row 3 to row 3. Okay, this is the operation I'm doing. And if I do that, I end up with what? I end up with, so let me copy that again. So instead of writing, I need to, okay, wait a minute. Copy. Come here. Paste. Okay, so what am I doing? So if I do that, I will get 0 here, right? This line will be 0. And then what can I do? I can, I mean, I can do a little bit more work, but at the end, what I will get is, okay, so I can swap first 2 rows, row 1 and row 2. So if I do that, and later if I multiply the first row by minus 1, so what do I get? The first row becomes 1, minus 1 and 1, and then 0, and the second row becomes 0 and minus 2 and 1, 0, and there will be zeros here. Finally, I can do what? I can divide the second row by minus 1/2, or multiply it by minus 1/2. Then I get 1, minus 1 and 1, then 0, 1 and minus 1/2, and then 0, 0, 0. Okay. Okay, from here we can get the solutions. So only x1 and x2 have leading ones. x3 does not have a leading one, so I call it as a free parameter. x3 is free. It can be anything, but once I fix it, I get x2 as what? x2 will become 1/2 or r/2, right? What about x1? So I know that x1 minus x2 plus x3 equals 0, which would give me x1 minus r/2 plus r equals 0, which will give us x1 equals what? x1 equals minus r/2. Okay, we found the eigenvector, right? So eigenvectors of lambda equals 1 are what? They are of this form. So minus r/2 x1, right? x2 is r/2 and x3 is r. Or I can write this as r times minus 1/2 minus 1 or plus 1/2 and 1. Here r is not 0, r is any number other than 0. Okay, so there are infinitely many eigenvectors of lambda equals 1, and all of them have this form. So you see, eigenvectors are not unique. There are infinitely many of them. Okay, so that's always something that's appearing. We could also write, so instead of this, we could write the eigenvectors of lambda equals 1, maybe in a slightly more easy way. So we could write some r, or let's write s, times minus 1, plus 1 and 2. And s is not 0, okay? So eigenvectors could also be represented in this form. Maybe it's more good looking, right? It's a better looking representation of the eigenvectors. So both of these things are fine. Another way to write. Another way to write is eigenvectors can be represented in this form. Okay. Any questions, guys? Okay, so eigenvectors corresponding to eigenvectors of lambda equals 2 and lambda equals 3 can be found in the same way. Since it will take too much time, shall we do one more or maybe not? Okay, so I leave them as homework, okay? So these are homework. Please try to do them. And the answers are in this example in the book, example 12 from section 7.1. Any questions? No questions? Okay. No questions. Then let's look at another example. Again, a 3 by, or let me first consider a 2 by 2 example. Let's consider A equals 0, -1, and then 1 and 0. Okay, let's try to find eigenvalues and eigenvectors. And eigenvectors. Okay. Okay, so let's do step by step. The first step is to find the characteristic polynomial, right? Find the characteristic polynomial. So what is the characteristic polynomial? Characteristic polynomial is determinant of lambda I, this time I is 2 by 2, minus A, equals, so this is called the characteristic polynomial, P lambda. So if I write this, what do I get? I get determinant of lambda minus first component of A, then -1, then no, +1, then -1, then lambda minus 0. Okay, so I'm just so this is simple computation. And what do I get? I get determinant. So what is this determinant? This determinant is product of diagonal elements is lambda square minus the product of off diagonal elements is -1, so it will become +1. This is the characteristic polynomial. Then we find a second step maybe. Find the roots of this characteristic polynomial. So P lambda equals lambda square plus 1 equals 0. Okay, so when we are computing eigenvalues, we are not only interested in real roots, okay? So this is this is an important place where complex numbers must appear. we're not only interested in real roots of this equation, but we're also interested in complex roots of these of this characteristic equation. And I will try to explain the reason later when we are seeing some applications of it. So what does this mean? This means we have the roots are lambda square equals -1. And I'm hoping that you have seen something about the complex numbers. I hope. Hiç görmeyen var mı kompleks sayıları arkadaşlar? Umuyorum herkes birazcık olsun görmüştür. Çok fazla yapmayacağız ama. So lambda square equals -1 has the following two roots. Lambda 1 equals minus square root of -1. Okay. And the second root is plus square root of -1. Lisede görmüştük. Okay. So these two numbers are something called imaginary numbers. It's not a very good name because every number is imaginary. So, oops. Sorry. Every number is imaginary. Where was I? What happened? Oh, it didn't. Okay, so I was here, right? So I have these two roots, minus square root of -1, and the second guy is plus square root of -1. So these two numbers appear a lot. So they have a special name called imaginary numbers, as I said. So they are denoted by some letters, okay? Especially like electrical engineers deal a lot with them. So this is called minus I. So let me use this letter. So this is, so square root of -1 is called I, okay? So there is no real number whose square root is -1. So we give a special letter for this one. So this is also called the letter I. We have these two eigenvalues. Okay. So the eigenvalues are complex numbers in this case. Lambda 1 equals -I and lambda 2 equals plus I. So any questions here? Okay, we do the third step. What is the third step now? Third step is so for each eigenvalue we try to find the corresponding eigenvector. So let's first consider the first eigenvalue, which is -I. Then what do we do? So we go back to this matrix, this one, and we write the corresponding equation. So instead of so I take this one, let me copy it. Okay, I take this matrix, copy, and paste here. Okay, so instead of lambda, what do I write? I write, in this case, -I, right? So I write -I, and I raise this guy and I write -I. Okay, and then I write x1, x2 here, and make it equal to 0. So the eigenvectors are solutions of this equation. Okay, so if I write this in the augmented matrix form, -I, -1, +1 and -I, and 0 and 0. Okay, So as always, we expect these two equations to be dependent. Okay, they shouldn't be independent, because if they are independent, then that means there's only 0, 0 solution. So these two equations will have infinitely many solutions. Okay, that's how we found these numbers actually. So these are the only numbers for which the corresponding equations have infinitely many solutions. So for any other value of lambda except for these two values, this equation, or like so if there was lambda here, so the corresponding equation has only the trivial solution, 0, 0. Okay, so how do we solve this one? So basically the second equation, we are expecting it to be a multiple of the first equation, right? So you see, if I multiply, okay, so what is the important relation about the number I? So the important relation about the number I is I squared is -1. Okay, so what do we get from here? So you see, if I multiply the first line by I, if I multiply the first line by I, what do I get? I get minus I squared, which is +1. So I times the first row plus the second row to second row. What does this give me? So this gives us maybe I should first swap the rows, right? That's better. So let's first swap these two rows, row 1 and row 2. If we do that, we will get -1 minus I, 0, and minus I and 1 is 0. Now if I do if I do I times no, minus I times row 1 plus row 2 to row 2, then what do we get? We get the first line does not change, but the second line happens what? So for the second line, I get minus I, and then minus I, so this will be plus I. And here I get 1, and if I multiply the first guy with minus I, it will be I squared, so this will be 1 minus 1. And I have 0, 0 here, and I get this matrix. Okay, let's go back. So this is the, so these numbers are 0. That's what we are expecting, right? So we have only just one equation. Okay, so our only equation is minus x1, and this time it was minus I times x2 equals 0. So there is no other equation, so x2 can be any number. So x2 is any number r. If I give it the name r, then x1 will be minus I times r. Okay, so what do I get from here? I get the eigenvector, which is x1 and x2, and which has the components minus I times r times r. Or I can write this as in this form, minus I times 1. Here r is any number other than 0. I don't want r to be 0. So these are the eigenvectors. Any questions here? Okay, these are the eigenvectors for the eigenvalue minus I, and the eigenvectors for the other eigenvalue for lambda 2 equals I. So if you, so I don't want to do the operations here, but if you carry on the operations, and you should end up with the eigenvector, which is basically the complex conjugate of this eigenvalue, okay? So in this case, we expect it to be r times what? R times complex conjugate of I is minus I, so the complex conjugate of minus I is I, and complex conjugate of 1 is 1. So it will be of this form. Here, R is any number which is, it can be also a complex number, okay? It can be a complex number. Okay. Any questions about this? Any questions? Okay, I think we have time for another example. So this time, let's do something with general linear operators, okay? So let's take L, which is a linear operator from P2 to P2. So P2 is the vector space of polynomials whose degree is less than or equal to 2. And let's suppose that L is defined in this way: AT squared plus BT plus C equals minus BT minus 2C. Okay, so this is, you can check that this is a linear transformation. It is given in the example, but you can check that this is a linear transformation. So let's try to find a matrix representation of this operator L with respect to the basis what is it? Let's suppose that this is 1 minus t and 1 plus t and t squared. So this is the first part of the question. Let's try to find the matrix representation. So how do you find the matrix representation of this operator L? So these are our these are our basis vectors. Let's call them as E1, the vector E1. Not E1, but maybe V1, okay? So let's call this V1, V2, and V3, okay? So these vectors will be V1, V2, V3. Let's use these three vectors. So what happens is we try to represent L V1 using these three vectors, right? So it will be A1 times V1, A2 times V2, plus A3 times V3. So what is this thing? So what is L of V1? L1 minus T. What is this? What is the value of for L1 minus T? So from the definition, we see that it is B is minus 1 here. So minus B is plus 1. So this is T. And minus 2C. What's minus 2C? It will be T minus 2, right? T minus 2. So I want to represent this using these three vectors. So it will be A1 times 1 minus T, A2 times 1 plus T, and A3 times T squared. So from here, we see A3 must be 0. If I look at the T coefficients, I get A2 minus A1 should be 1 because the corresponding T coefficients must be equal, and A1 plus A2 should be minus 2. Okay, so what is the solution for these two equations? So what is it? So A1, if I add these last two equations, I get if I get 2A2 equals minus 1, and A2 should be minus 1 over 2. And what about A1? A1 will be, what is A1? A1 will be minus 3 half, right? Okay, so what did we find? We find that, so how do we represent this? So we represent this in this way. So the coordinates of the vector 1 plus t with respect to this basis S is A1, A2, and A3, which we found to be what? We found this to be minus 3 over 2 and minus 1 over 2 and 0. So these are the coordinates of the this linear transformation with respect to this chosen basis S. And we can repeat the same thing with the other vectors, okay? So I don't think we have time. So if we go back quickly, so if we do this computation quickly, we get 1 plus t, the coordinates of L1 plus t with respect to this basis will become minus 1 half and then minus 3 half and 0. And then finally, let's look at the coordinates of t squared, right? So the last basis vector is t squared with respect to basis S. In this case, it is easy to see that this is, what is this? This will be oh, if you look at this, what is LT squared? LT squared is just 0, right? So this will be just 0, 0, 0. Okay, so the matrix representation of L with respect to basis S. So this is an ordered basis, right? We discussed about this ordered basis. S is the matrix whose first column is this vector minus 3 half, minus 1 half, and 0. And second column is the second, so this vector. And the third column is 0, 0, 0. Okay, so this is the matrix representation of this linear operator L with respect to this basis S. Then second part is find the eigenvalues and eigenvectors. Of this matrix, let's call this matrix A. Okay, so I don't think we have time to do this, but I will say something important here, okay? So the important thing I will say is this. So suppose we have chosen another basis of P2, not this one, but another basis. In this case, we end up with another matrix here. But what happens is, if we compute the eigenvalues and eigenvectors of that other matrix, they will be the same as the eigenvalues and eigenvectors of this matrix. The eigenvalues will be same, okay? So in a sense, these eigenvalues do not really depend on which basis is chosen. So it's something related to this linear operator, but not this basis, okay? So the end result, we will say that these are really the eigenvalues of this linear operator, not the matrix. My matrix is just a representation of that linear operator. It's just one representation, okay? So it has infinitely many representations. If you choose different bases, you end up with different representations. That's the important thing about matrices and linear transformations. So linear transformations are the real objects, and matrices are just their like images, their representations. Okay, so that's the interesting thing about this. So and the second thing is, at the end, you see, we always end up with a matrix, and what we are doing is really computing the eigenvalues and eigenvectors of that matrix. So I still didn't say anything about why this is important, but finding eigenvalues and eigenvectors is extremely important in all sciences. Okay, so I have been doing research for the last maybe, I don't know, 15 years. And all my life, I mean, maybe every day I'm dealing with these eigenvalues and eigenvectors. They are very important, at least for me, okay? So, and they are very important. They are very, very important in things like search algorithms, okay? So those Google ranking algorithms, right? So they are very related to this concept of eigenvalues and eigenvectors. So it's something very important, and I will talk more about it tomorrow. And next week we will do some more examples and then finish the semester. So this is our last 2 weeks, okay? Okay. Any questions? How did we understand L1 minus T is T plus 2? So from this definition, okay? So if you, so here 1 is basically C and B is minus 1. So it makes what does it make? So if I put minus 1 here, I get, so this will becomes plus T. And if I put C equals 1, I get minus 2. It comes from the definition, Ahmet, Emre, Sarcan. Okay? It's okay. Okay, yeah. Okay, so I plan to put this in the website, this PDF file, as a PDF file. You can check it from there, okay? Okay, guys, thanks for coming. See you tomorrow.